In 2019, a rock was picked up off the sand somewhere in the Sahara Desert. It was small enough to hold in one hand. Nobody knew what it was at the time. Nobody knew where it came from. It looked from the outside like 1,000 other meteorites sitting in collections and university drawers around the world. But last week, scientists at the University of Colorado published a paper confirming what the inside of that rock had been hiding for 4.5 billion years. It is a fragment of a planet that no longer exists. A world possibly as large as Mars that formed in the earliest chaos of our solar system, lived for a few million years, and was then destroyed so completely that we had no proof it ever existed until now. By the end of this video, you'll understand what this rock actually is, what it tells us about a chapter of solar system history that has never been directly seen, and why the people who study this say there are almost certainly more of these lost worlds sitting in museum drawers right now, waiting to be recognized. Let's get into it. The meteorite has a catalog name, Northwest Africa 12774. Scientists use the abbreviation NWA, which they attach to every meteorite found in that region, followed by a number. NWA 12774 is a type called an angrite, and the moment you understand what an angrite is and how rare they are, the significance of this discovery starts to become clear. Out of more than 80,000 meteorites that human beings have found and catalogued on Earth, 68 are angrites. 68. That is less than 0.1% of the entire meteorite collection of the planet. Every other category of meteorite, the iron ones, the stony ones, the ones from Mars, the ones from the moon, vastly outnumbers this class. Angrites are not just rare in the way that unusual things are rare, they represent something the solar system produced in almost vanishingly small quantities. And even within that already tiny group, NWA 12774 is strange in a way that immediately set it apart from the others. To understand what makes angrites unusual in the first place, you have to know one basic thing about how planetary science works. The chemistry of a rock tells you the environment it formed in. Temperature, pressure, what other elements were present, how long the rock spent underground before being exposed. Every mineral is a record of the conditions that created it. And what angrites record is a chemistry so different from the rest of the solar system that it has puzzled scientists for decades. The most common ingredient in nearly every rocky planet in the solar system, in Earth, in Mars, in Venus, in the rocky asteroids, is silicon dioxide, silica. It is the same material that makes up sand and quartz and most of the ground beneath your feet. It is everywhere. But angrites contain almost none of it. Their chemistry is alien compared to everything else in the solar system. No silica, unusual mineral ratios, a composition that does not match any known asteroid and does not match Earth or Mars. For a long time, scientists assumed that since these rocks had to come from somewhere, and since the most obvious origin for any meteorite is an asteroid, angrites must come from some unusual asteroid with an unusually strange makeup. That was the working assumption for decades, and it was wrong. The clue that broke the assumption open was sitting inside NWA 12774, and it came down to a single mineral and the amount of aluminum trapped inside it. The mineral is called clinopyroxene. It is commonly found in the crust and mantle of rocky planets, including Earth. Under normal conditions, on a small body like an asteroid, clinopyroxene forms with a certain chemical signature. But the clinopyroxene inside NWA 12774 was not normal. It was extraordinarily rich in aluminum. Off the charts was how the lead researcher, Aaron Bell, described the aluminum content when he talked to journalists after the paper was published. And that off-the-charts aluminum content is not a curiosity, it is a measurement. Because aluminum builds up inside clinopyroxene only when the rock forms under enormous pressure deep inside a large body. Pressure inside a planetary body works exactly the way you would expect. The deeper you go, the more rock is piled above you and the harder it pushes down. A small asteroid with a radius of 100 or 200 kilometers does not have enough mass to generate very much pressure even at its core. But a large planet-sized object, something with the mass of the Moon or Mars, generates crushing pressure in its interior, enough to force aluminum into crystal structures in ways a small body simply cannot replicate. The aluminum content inside that crystal was a geological fingerprint left by the conditions of formation, and those conditions required a body far larger than any asteroid. Bell and his colleagues built a calculation tool, a geobarometer, designed to take the mineral chemistry of a rock and work backward to the pressure at which it formed. When they applied it to NWA 12774, the minimum pressure that could explain the aluminum content was 17.5 kilobars. To put that in terms that mean something, 17.5 kilobars is roughly 17,000 times the air pressure at sea level on Earth's surface. That is not a small body, that is not an asteroid. To generate 17.5 kilobars of pressure inside a rocky object, you need a body with a radius of at least 1,000 kilometers. That is larger than Pluto. It is close to the size of the Moon, and the crystals may point to something even larger. The researchers estimate the parent body, the world this rock came from, could have had a radius somewhere between 1,000 and 3,300 kilometers, putting the upper end comfortably in the size range of Mars. Here is what that means in full. Somewhere in the inner solar system, more than 4.5 billion years ago, there existed a world as large as Mars or larger, made of materials fundamentally different from the ingredients of Earth, with its own interior differentiated into layers, its own core, its own magma processes happening deep underground. A distinct planet on its own evolutionary path, forming in the same neighborhood as the rocky planets we know today, and we had no idea it existed. Not even a suspicion. For all of the history of astronomy, for every measurement taken of the solar system, for every model built of how planets form and evolve, this world was missing from the picture entirely. A planet-sized gap in the origin story of our solar system that we had never even noticed was empty. That changes with this paper, because that rock, NWA 12774, a small fragment the size of something you could slip into your coat pocket, is the first direct physical evidence that this world ever existed. Without it, the planet is simply absent from the record. With it, a lost world re-enters history. To understand why it is lost, you need to understand what the early solar system actually looked like, because it looked nothing like it does today. Most people have a picture of the solar system as a settled, predictable place with a fixed number of planets on stable orbits, roughly in the arrangement they are in now. But that arrangement is the end product of an enormously violent process, not the starting condition. The solar system we see today is the survivor of a period called the Era of Planetary Formation, roughly the first 100 million years after the Sun ignited, when the disk of gas and dust surrounding the young star was actively condensing into objects, and those objects were actively colliding with each other. The early solar system was not a neighborhood with a fixed number of residents. It was a demolition derby. Hundreds of planetary embryos, objects ranging from a few hundred kilometers to the size of the Moon, were forming and growing and colliding and merging and shattering. The modern terrestrial planets, Mercury, Venus, Earth, and Mars, are the ones that survived this process, the ones that happen to end up on stable orbits or that happen to be large enough to absorb the impacts they received. But they were not the only large worlds that formed. By the best models of this era, there were many more planetary embryos in the early inner solar system than survived to become modern planets. The ones that did not survive either merged into the planets we know, were flung out of the inner solar system by gravitational kicks from Jupiter, or were shattered in collisions and broken back into debris. The solar system erased most of the evidence of its own early population. The demolition derby cleaned up its own wreckage. That is the context in which the angrite parent body lived and died. It was one of these early planetary embryos, large enough to develop a layered interior with real geological processes, but unlucky enough to be in the wrong place when the chaos of that early era reached it. At some point, the most likely explanation is a catastrophic collision with another large body. It was destroyed. Its pieces spread through the solar system. Some of those pieces settled into the asteroid belt, where a handful of them were gradually nudged onto Earth-crossing orbits over the following billions of years. And eventually, some of them fell through Earth's atmosphere and landed in deserts, where they sat until someone picked them up. The timeline matters here because it puts this world in a specific window of solar system history that most people have never heard described in detail. The angrite meteorites, including NWA 12774, are among the oldest known volcanic rocks anywhere in the solar system. Their ages date to within the first few million years after the solar system began forming, roughly 4.56 billion years ago. That is almost immediately at the start. The solar system was barely a disk of condensing gas and dust when the angrite parent body was already large enough to have geological activity, already large enough to have a layered interior generating the pressures that show up in those crystals. It formed fast, lived briefly by geological standards, and was gone before the planets as we know them had even finished assembling. Earth itself did not reach its final size until tens of millions of years after the angrite parent body had already ceased to exist. This is the picture that the research keeps forcing into view. The solar system in its first 10 million years was nothing like its final form. It was populated by a generation of worlds that formed quickly, evolved quickly, and in many cases died quickly, destroyed by the collisions that would eventually leave the current 8 planets as the sole survivors. The angrite parent body belonged to that first generation. It may have been, in a real sense, one of the first true planets, one of the first large worlds to form a layered interior around the young sun, before Earth existed, before Mars existed, before the arrangement of the solar system had taken anything like its current shape. And it was gone before that arrangement was complete. Which is exactly why there is no trace of it in any sky survey, no gravitational signature, no orbit, no name on any chart. It exists only as chemistry, logged into crystals, preserved in fragments scattered across the inner solar system, and occasionally falling to Earth. This is the part of the story that tends to get lost in the excitement about what was found. The planet was destroyed. It does not exist anymore. You cannot point to it in the night sky. It has no orbit, no position, no name on any star chart. The only reason we know it existed at all is that a few of its fragments happened to survive 4.5 billion years of space travel and happened to land on a planet with scientists on it who happened to pick them up and look closely enough. The research team leader said it directly after the paper was published. We only know it existed because a few fragments of it happened to land on Earth. That sentence is worth sitting with because it is not a figure of speech. It is a precise description of how fragile the entire chain of evidence is. And here is the part of this discovery that makes it genuinely bigger than just one meteorite and one lost world. If this world existed and left behind fragments we did not recognize for decades, the logical question is, how many others are there? And the answer, based on everything the researchers are saying publicly, is probably several. There are roughly 70 angrites total in collections around the world, and scientists have now found that at least some of them, the ones with the right primitive compositions, point toward this same large parent body. But beyond angrites, there are other categories of unusual meteorites whose origins are still debated, still attributed to generic asteroids because nobody has looked carefully enough at the pressure signatures in their minerals. Bell said it plainly at the end of the paper. There are many meteorites sitting in drawers that have not been thoroughly studied, and there were likely more of these protoplanets we do not know about yet. That is not a hedged statement buried in a conclusion. It is a scientist telling you that the solar system almost certainly had more large worlds in its early history than we have accounted for, and that the evidence for some of them is already in the collections. It is already here. It has been here for years, waiting in labeled drawers in university basements, not identified for what it is because nobody ran the right measurement yet. The reason this discovery matters beyond the individual scientific result is what it says about the origin of the planets we do live on. The researchers found that the material the lost protoplanet was made of is fundamentally different from the ingredients of Earth and Mars. Different silica content, different mineral ratios, a chemistry that suggests a completely separate path of planetary formation. This was not a failed version of Earth. It was something else entirely. A planet built from a different recipe on a different evolutionary road in the same solar system at the same time. If that planet had not been destroyed, the inner solar system would look entirely different from what it is today. The arrangement of planets we think of as permanent, the arrangement that made Earth habitable and placed it at exactly the right distance from the Sun, was not inevitable. It was the result of a series of violent collisions among worlds that no longer exist, and the survivors happened to end up where they are. Some of the debris from the lost world, the researchers note, may have become part of Earth. When a large body is shattered in a collision in the early solar system, its material does not vanish. It disperses as fragments, and those fragments eventually get incorporated into whatever objects are growing nearby. Earth is thought to have been assembled partly from the debris of other large bodies over hundreds of millions of years of impacts. Some fraction of the material inside Earth right now may have originated inside a planet that existed before Earth did, a planet that we have now, for the first time, found direct evidence of. There is one thing this paper does not answer, and it is worth being honest about it. The researchers do not know exactly how the protoplanet was destroyed. The most likely explanation is a catastrophic collision with another large body during the chaotic early solar system, but they cannot prove the specific event. They know the object had to be large because of the pressure signature in the crystals. They know it no longer exists because there is nothing in the solar system today that matches its chemical profile. They know it formed within the first few million years of the solar system's existence because the angrite rocks are among the oldest non-volcanic rocks anywhere, dating to almost exactly the beginning. But the specific moment of destruction, the collision itself, that is a chapter of the record that has not survived. Whatever hit the angrite parent body and shattered it was itself either destroyed or merged into another object, and the evidence of the impact is lost in the noise of 4.5 billion years of subsequent history. What has survived is the fragment, NWA 12774, a small rock pulled from a desert that contains inside its crystals a pressure signature that was set the moment it solidified, deep in the interior of a world that no longer exists. The geology of a lost planet, preserved in a piece of rock small enough to hold in your hand, found on the surface of a different planet entirely. That is what this paper is about, and that is why it matters. The questions it opens are as interesting as the question it answers. If the early solar system contained several Mars-sized planetary embryos that were later destroyed, how much did those worlds change the composition of the surviving planets? How much of what makes Earth chemically unusual compared to other rocky bodies is the result of inheriting material from worlds like this one? And how many of those worlds are still waiting in the meteorite collections, unidentified, catalogued under a different assumption, sitting in a drawer until someone runs the right test on the right crystal? Those are the questions driving the next phase of this research. Bell and his team are not done. The paper explicitly points towards studying other angrite meteorites with the same geobarometric method, looking for more pressure signatures that could not have been generated by a small asteroid. If more of the 70 known angrites turn out to carry the same fingerprint, the picture of the angrite parent body sharpens. If they find meteorites in different classes that carry similar signatures, the count of lost worlds in the early solar system could grow. This is how planetary science works at its edge, not with a single revelation that settles all questions, but with a measurement that opens a new line of investigation and makes a hidden chapter of history suddenly accessible. For decades, the chemical strangeness of angrites was a puzzle with no clear explanation, because the question being asked was the wrong one. Scientists were asking which asteroid did these come from. The right question, the one this paper finally asks and answers, is whether they came from an asteroid at all. The answer is they did not. They came from something far larger, something that died before most of the solar system as we know it was finished forming. And a rock picked up in the Sahara in 2019 is the proof. There is a direct line from that discovery to a question about every meteorite in every collection in the world. What else have we been misidentifying? How many other rocks have been catalogued as asteroid fragments because that was the simplest explanation, when the right measurements would tell a different story? The tools to find out exist now. The geobarometer Bell's team built is not exotic or unavailable. It is a method that can be applied to other samples with the minerals and the equipment that universities already have. The bottleneck is not capability, it is attention. It is the systematic decision to look at already collected rocks through a new question. Some of the most important discoveries in planetary science in the next decade may not come from new missions to asteroids or new telescopes scanning the sky. They may come from existing meteorite collections that have been sitting in storage for years, waiting for someone to ask the right question about the crystals inside them. NWA 12774 is what happens when that question finally gets asked. A lost planet re-enters the record. An entire world, unknown for 4.5 billion years, confirmed in a paper published last week from a fragment of rock no larger than what you could pick up off the ground. We will be tracking this as it develops.